Good morning. Welcome to this next lecture on sound and structural vibration. Last time we stopped at this juncture where we found the uncoupled plate vibration. Okay. So now we are going to find the uncoupled acoustic response. Okay. Uncoupled acoustic response. The acoustic potential was given by phi of x comma y equal to a e to the power of I k x x plus I k y y, also given in terms of gamma a e to the power of I k x x minus gamma y. So gamma and ky are related in that manner. Okay. The acoustic particle velocity, okay, at the plate surface, which is v a x comma 0, is given by del phi by del y at y equal to 0, okay, and that is equal to I k y a e to the power of I k x x. Now this is equal, it is equal to the plate velocity. V of x. Okay, and we just found the plate velocity. What was that? V of x was given by omega f by 4 kp cube b e to the power of I k p x plus I e to the power of minus k p x for x greater than 0. Okay. Now there are two terms here and we have to find the sound field related to both, but for the moment, for x much greater than 0, okay, there is a decaying component. This component is decaying. Okay, so we'll ignore that component. The decaying or evanescent decaying component vanishes. So for the time being we'll ignore it. Okay. So my V of x is finally omega f by 4 kp cube b e to the power of I k p x. Okay, and that is equal. So this is at the surface, there is a plate velocity, it's a surface obviously, and this is equal to I k y a e to the power of I k x x, the acoustic particle velocity at y equal to 0. And of course we know that Kp must be equal to Kx, right? The plate wave number must be the x wave number of the acoustic field, okay? And therefore A turns out to be equal to omega f by IKY 4 Kp cube into B, okay, which means what? My phi of x comma y is given by minus I omega f by ky 4 Kp cube B e to the power of I Kpx plus I Kyy for x much greater than 0. Okay. If we want for x much less than 0, okay, we have phi x comma y is equal to minus I omega f by 4 Kp cube ky into B e to the power of I minus Kpx plus I Ky 1. Okay. Here we have Ky given by square root of K0 square minus Kp square when K0 is greater than Kp, okay, and Ky is equal to I square root of Kp square minus K0 square when Kp is greater than K0, below coincidence. Okay, so below coincidence, the sound field, sound decreases in the y direction. Okay, this I and this I will make it minus and Kyy will decrease in the y direction. Okay, now what do we have? We have essentially a Kx wave number which is Kp, okay, and a Ky wave number, okay, and both combine to give me the acoustic wave number K0, okay, and this angle is theta. Okay, so what we can write is we have Kpx as the phase part for x, we have Kyy for the phase part of y, so we have K0 cos theta x plus K0 sin theta y as the expression, okay, for the propagator. Okay, so the sound field in the case of propagation moves as a plane wave at an angle theta, they are plane waves at an angle theta to the plate. Okay, so K0 is normal to the wavefront, okay, and makes an angle theta with the plate. Okay, this is the part related to the propagating portion of the plate response. Okay, and that's the dominant response at larger and larger values of x. Okay, but there is a decaying component. There is a decaying component. Okay, so what is that? That is V of x is equal to omega f by 4 kp cube b I e to the power of minus kp into x. Okay. Now phi was given as what? X comma y is equal to a e to the power of minus kp into x plus I k y y. Okay, we can also write it as a e to the power of I k p into x plus k y y. Okay. Now what is ky? What is ky? Okay. What I have, the basic wave equation again will give me this squared plus this squared should be equal to my acoustic wave number. So I will get ky squared minus kp squared is equal to k0 squared, or rather now ky square is equal to k0 squared plus kp squared, which means ky is equal to square root of k0 square plus kp square. Okay, which means my phi x comma y is sum a again from the velocity I k p x plus square root of k0 square plus kp square into y. Okay, a of course given by I omega f by 4 kp cube b. Okay, now what has happened? Okay, what has happened is this. I have a decaying field from here on the plate. Okay, from the forcing location I have a decaying field. Okay, this is the velocity field. Corresponding to that I found the acoustic field, and what does it say? The acoustic field has an amplitude and a decaying component just as the plate, but it has a propagating component in the y, k0 square plus kp square y, because my time is this. So the decaying velocity field has produced a propagating field in the y direction. Okay, in some sense it's not significant because we said we are looking at far field. However, if you look at a wave coming in on a plate and a discontinuity placed over here, okay, like a rib, okay. So the common sense says that presence of a rib, improves impedance, creates discontinuity, reduces vibration, reduces the sound. It's a common sense idea. It's well worth looking into, of course, okay. But now watch here, the same thing, a kind of a discontinuity or a rib placed here, okay, produces a propagating component of a sound field, okay. This decays a wave in the x direction, but there is a propagating component due to a discontinuity. That's what this tells you. So it's not always true that if you rib a vibrating plate you will get reduction. You have to keep this fact in mind, that at a discontinuity there can be a y direction propagating field, okay. So that's the sound field due to the decaying part. So the sum of the fields is both, okay. So that closes the sound field which is uncoupled acoustic field, okay. Now we have found that my coupled response, both which is the main interest for us in this problem, the coupled response both in velocity and potential are given by V of x is equal to 1 over twice pi integral minus infinity to infinity minus I omega f e to the power of I kx over b k fourth minus kp fourth minus mu kp fourth by gamma, okay. Gamma has the form, gamma specifically has the form square root of k square minus k0 squared. Similarly, the phi, okay, x comma y is given by 1 over twice pi integral minus infinity to infinity I omega f e to the power of minus gamma y e to the power of I kx over b k fourth minus kp fourth into gamma minus mu kp fourth. Now before we get into integrating these, we have to look at the gamma issue. Gamma is a square root function, okay, and we are going to resort to integration in the complex domain, in the complex plane. Okay. Now to give you a taste of this, if I have a function, okay, complex function, if I have a complex function, let's say f of z, and it has nice continuous analytic functions, let's say some g of z, but it has a square root of z also. Okay. So now let us look at it, this function f of z in the complex plane. G of z is well behaved, okay, so it doesn't create any problem. But look at z to the power half. Okay, so look, so at this point, suppose I am going to integrate on a circular arc, full circular, suppose I am going to integrate, okay. So my z, this z, okay, is what parameterized as z equal to r e to the power of I theta, and theta, let's say 0 less than twice pi. Okay. Now just above 0, my z, the independent variable, is r. So let's say this is r e to the power of I0, which is r, okay, and z at r e to the power of I 2 pi is equal to r. So this independent variable is continuous. Now look at the function, which is z to the power half. At z with theta 0, okay, we get z to the power half as r to the power half, okay. But at z with theta 2 pi, okay, that means you have come full circle, z to the power half is r to the power half e to the power of I 2 pi by 2, which is minus r to the power half. So as my function goes around, goes around the circle and comes back, the functional value z to the power half here to z to the power half here has changed sign. It's discontinuous, okay, and that is the result of square root. Okay, so now gamma has a square root in it, both in velocity and acoustic potential. So we have to first find a branch in the complex plane for gamma to be continuous. Okay, because we will finally use the Cauchy residue theorem, and it requires that the function be continuous and analytic in most of the region except at isolated singularities. So we have to find a branch where gamma is going to be continuous. Okay. In addition, my phi had, let's say phi at x equal to 0, I mean y equal to 0, had something like a e to the power of minus gamma into y and e to the power I k x x, and of course time if you want to put time. However, the y function, the y propagator was like this. Okay, so now if gamma is real, we want the sound field to decay in the y direction. Okay, so then gamma must be positive. Okay, whereas if gamma is imaginary, then gamma must be negative imaginary. Okay, what does that do? Negative imaginary makes it phi x comma y is equal to a e to the power of I something y into e to the power of minus I omega t, which is a positive y propagating field. Okay, if gamma is imaginary and we take the positive square root, that means positive I something, it means there is a incoming, okay, negative coming or incoming field, incoming sound field or incoming wave from infinity. Okay, that means there is a plate vibrating, but there is a sound field coming towards it from infinity, which is not possible, and therefore the negative sign has to be chosen when it's imaginary. And for a similar reason, the positive value must be chosen when it's real, so that the field is decaying. If we choose the negative when it is real, it will imply that this is blowing up in the y direction. So at infinity it actually blows up. So both are a must. These two are physical conditions that have to be imposed on gamma. Okay, so one is we have to choose a branch such that gamma is continuous. That's one. Okay, so there are several ways to choose a branch that gamma is continuous. In addition, such a branch has to be chosen where this is also valid when k is moving on the real axis, and k moves on the real axis. These two conditions should be valid. Okay, so we will look at the square root function in the complex plane to get an understanding. Okay, so let me stop here for today for this lecture. We will continue from there in the next class. Thank you.